Hi, today we're going to talk about uniform circular motion. The word uniform in this phrase means constant speed. There is non-uniform circular motion with changing speeds, but that's not what we're going to deal with at this level. Okay, so we're going to deal with only constant speed. And if you know the constant speed equation, right, v equals displacement over time, right, the average speed equation, think about how things move in a circular path. It's going to cover a definite circumference, right? And then it's going to cover that circumference in a specific amount of time, which we call the period. The period is the time for one cycle. Okay, so this is a period, and that's the circumference. You can easily calculate your average speed. If you look along the radius, which of these, right, these points are moving the fastest? If you look at this equation, if the period is the same, then the one with the biggest radius is going to have to cover the most distance in the same amount of time. So this 0.5 has to cover all this distance. So if you're on a merry-go-round, the most thrilling place to sit is all the way on the outside. The inner horses are not so much fun, but might be more appropriate for smaller children. Velocity, this speed here, always points tangent to the circle. Okay, so if there was a string attaching something to move in a circle, right? If you had a ball at the end of a string and you were whirling it about, if the string broke right here, it would go in this path. So this is called tangential velocity. A tangent to a circle is not the same as the trig function. Tangent to a circle means it touches the circle at one point, and so that is the direction of motion at that particular point. Since you're moving in a circle, this direction is always changing. Sometimes that way, that way, that way, right? And as you go around, tangent to the circle changes. Therefore, even though your speed is constant, your velocity is not constant. And since velocity is not constant, there must be an acceleration. This acceleration has a special name. It's called centripetal acceleration. So when you're moving in a circle, there must be an acceleration because the velocity is always changing. If there must be an acceleration, which way does it point? It always points perpendicular to the circle itself, to the velocity. It points to the center of the circle. Okay? So tangential velocity is always perpendicular to the centripetal acceleration, even though I didn't draw it so great right there, right? But it should be. Always points to the center. If there's no centripetal acceleration, you cannot be moving in a circle. So acceleration can never equal zero. And since acceleration can't equal zero, what else can equal zero? Well, let's talk about centripetal force. When things are moving in any path, right, the first law of motion says that an object in motion will stay in motion at constant speed in a straight line. But this is not moving in a straight line. Naturally, things move in a straight line. We've got the constant speed part, but we don't have the straight line part. So then what is required? The rest of Newton's first law says, unless there's an unbalanced force acting on it. So here is the unbalanced force. It's called the centripetal force. In order to move in a circle, you must have a centripetal force, just like you must have an acceleration. Otherwise, you're not going to change from your straight line motion. And that's why if this centripetal force pulling to the center is gone, you will continue in a straight line path tangent to the circle. So we have three equations that we use very commonly here. We have the centripetal acceleration equation. This is the only new one we have. Acceleration equals tangential velocity squared over the radius. You are not allowed to use the linear kinematics equations for this type of stuff because those are linear. This is not linear. This is two-dimensional motion, and you can only use this, which makes it so much easier. You don't have to worry about which equation to use. This is the tangential velocity equation, or the speed equation. It's a linear quantity, but it's only for that particular point. But since we're moving at a constant speed, will work fine for us. This is just displacement over time. So not really a new equation, just applying it to some specific circular information. We'll still use Newton's second law, right? We're going to apply it specifically to circular motion by putting a subscript c to stand for centripetal, right, for both the force and the acceleration, and you get centripetal force, net centripetal force equals mass times centripetal acceleration. We can combine all of these. You can plug this in here, and this will be mv squared over r. You could put the velocity in there, and you get 4 pi squared r over t squared. So you can combine these and derive other formulas. I tend to leave them separate. I think it's just makes more sense in my head. So here's a typical basic problem. So a 0.2 kilogram ball is tied to the end of a 0.5 meter long string. You whirl it above your head like this, so it makes a horizontal circle like this, right? It takes 6 seconds to make 24 revolutions. What is the tension in the string? So 6 seconds to make 24 revolutions. These are 24 circumferences in 6 seconds, but a period is just 1. So what you have to do to find the period is to do 6 seconds over 24 revolutions will tell you how a quarter of a second per rotation. That's the period. So here's my little sketch. Here I found the period. I drew my little free body diagram. So I have net force, centripetal force equals MAC. I want to find the tension force. It's the only force acting towards the center of the circle. Well, what happened to the weight force? Weight is acting down into the board. I can't even draw it because it goes into the board. It's the wrong point of view. Regardless, it's not on my centripetal axis, so I don't need to worry about it for this problem. Are there problems where we will? Yes, but not right now. So tension equals m, and then I put v squared over r in place of centripetal acceleration. My problem is I don't know v. I know m, I know r, and I want this, but I don't know v. So I have to go find that. So to find tangential velocity, I need 2 pi r over the period, and you're given the radius, you have the period that you solved for here, so you could find the tangential velocity and just plug that in. So then you could solve for the force. Can you put all the variables together and just solve at the end? Yes, that would be fine also. The thing most people have trouble with is making predictions about relationships. And the equation is not just for the math. It will help guide your thinking. And so when a very common type of question is, what effect does doubling the radius only have on the net centripetal force? It could be for anything. When you're driving a car, doubling the radius of a turn. When you're spinning a ball, doubling the radius of that ball. You're on a roller coaster, doubling the radius of a big loop. That's the question. What happens? So if you look here, if you double this number, then you have a smaller centripetal force. A smaller centripetal force means that there's less tension or less normal force or whatever, less friction required. So it depends on the problem if that's a good or a bad thing. It could be either. If you double the speed, and by only I mean leaving everything else constant, if you double this, if you double the velocity, but velocity is squared, that's the same as quadrupling the net force. So you need 4 times the force if you're going double the speed. That's why it's really important as a driver to slow down as you enter a turn. If you double the mass, well, that's a direct relationship, so you're going to just double the centripetal force needed. So a heavier car requires more friction to make the turn than one that's not.